This video gives an introduction and overview of the architecture of the Blitz-64 processor core. In this video, we'll go over the instruction set architecture of the Blitz-64 core. We'll talk about the general purpose registers. We'll talk about how machine instructions are represented. We'll go over the control registers. We will talk about the protection and privilege mechanism that the kernel uses. And we will talk about virtual memory and how page tables are implemented in the Blitz-64 core. Let's begin with the general purpose registers. In Blitz-64, there are 16 general purpose registers, and they are each 64 bits in size. The registers are named R0 through R15, and in addition, some of the registers have a second name that can be used that's a little bit more intuitive. Register R0 is hardwired to 0, and it can be used in a machine instruction as the destination when the result is not needed. It can also be used as a source in an instruction if you want 0. R1 through R7 are used to pass arguments to a function, and if the function returns a value, that would be returned in register R1. Register 8 is also called the T register, and that's a temporary register used by the assembler and linker in processing synthetic instructions. This would typically be avoided by programmers. Registers R9, 10, and 11, also called S0, S1, and S2, are general purpose work registers that can be used within a function. These registers are caller saved, as well as registers R1 through R8. And what that means is that if some code cares about these values, it had better save that register before calling a function, and then restore the value of that register after the function returns. Functions are, by convention, allowed to update and modify any of these registers, and so the caller must save the value if it's important to the caller. Register R12 is called the thread pointer. This is usually constant throughout the execution of an individual thread, but several threads in a single program might have a different thread pointer value. The thread pointer points to a data structure that contains a number of constants or variables that are specific to that particular thread. Register 13 is called the global pointer, GP, and that is usually constant throughout the existence of the program and would be the same for all threads within that program. This just makes addressing easier and is used to access variables and static data. Register R14 is called the link register, and that's used when a function is called. The return address is saved in register 14, the LR register. Finally, register 15 is the stack pointer, and that is used for the stack of stack frames that are allocated whenever functions are called. Now let's look at how machine instructions are encoded in the Blitz architecture. There are two encoding schemes, the full-sized encoding scheme and the compressed encoding scheme. Every full-sized instruction is 32 bits in length. The compressed instructions have a variable byte length encoding. The first 2 bits of the instruction tell whether it is a full-sized instruction or whether it is a compressed instruction. Every machine instruction has a full-sized encoding. In addition, some of the more commonly used instructions have a compressed encoding, and this improves execution efficiency. There are 4 different formats of instruction encoding in the full-sized encoding scheme: format A, B, C, and D. In format A, the first byte is all zeros, and the opcode is in the second byte. So with 8 bits here, we have up to 256 different format A instructions. With format B, C, and D, the first byte will be non-zero, and that gives us up to 63 possible instructions in the format B, C, and D category. In the format A instructions, there are also 4 fields of 4 bits each. 4 bits is exactly the right amount to encode one of the 16 general purpose registers. There's a field for the destination register as well as up to 3 source registers. Not all instructions will use all these fields, but all the fields are in the same spot in a Format A instruction. With Format B, we have only a destination register and a source register, which may or may not be used. And we also have a 16-bit field, which will contain an immediate value. This can range from approximately minus 32K to plus 32K. So it's a pretty wide range of possible values. In Format C, we also have a 16-bit field. It's split up a little bit here. And instead of having a destination register, we also have space for 2 source registers. And finally, in the Format D format, we have only a destination register and an immediate value, which is 20 bits in length. In addition to the 16 general purpose registers, the Blitz architecture also has 16 so-called control and status registers, and these are also 64 bits in length. These are used by the operating system kernel, and therefore they're privileged and must be protected. A Blitz processor is running in one of 2 modes at any point in time. There is user mode and there is kernel mode. User code executes in user mode, and any code that's running in kernel mode is by definition part of the operating system kernel. The instructions that access these control and status registers are privileged, and privileged instructions may only be executed when running in kernel mode. To the user mode code, these registers are essentially invisible and inaccessible. Since there are 16 of these registers, they can be encoded with a 4-bit field, and that works nicely with the instruction fields that I showed earlier in these instruction formats. Each of the control and status registers has a different function and slightly different behavior in the hardware. So let's go over these registers one by one. First of all, each register has a specific and unique name, such as CSR version or CSR status, and this is the name that would be used in any assembly code instruction that references the register directly. There are privileged instructions to read and to write these registers directly. The first 5 registers are read-only, so any attempt to store into them directly is ignored. The remaining registers are read-write and can be updated directly. Over time, an instruction set architecture will grow and will mutate. The CSR version register contains information about which version is being implemented by the particular core. In addition, there could be some optional features, and so bits within this register will indicate which optional features are or are not implemented. The product identifier register contains a couple of fields. One indicates which manufacturer created the core, and the remainder of that register contains manufacturer-specific information. This could be information about which product within their line of products this is. It could even be a particular serial number. In a multi-core system, kernel code will need to know which core it is running on, so the core register will contain that information, as well as information about which other cores might or might not be available. The instruction register will be incremented automatically after each instruction is executed, and the cycle register will be incremented once every clock cycle. Both of these two are reset to 0 on power up. From time to time, there will be a timer interrupt, and the kernel will use that to implement time slicing. So the timer register is used to schedule the next timer interrupt. Then we have the all-important status register, and that has several different fields which are shown here. The first bit here indicates whether the core is running in kernel mode or user mode. The next bit indicates whether interrupts are enabled or disabled. This bit indicates whether single stepping should be occurring. And then we have 2 fields for floating point. This 2-bit field here determines how rounding is to be done by the floating point instructions. And this 5-bit field here contains bits that are set after floating point instructions to determine whether, for example, overflow occurred or not. These bits are unused, and this is the address space identifier. Each virtual address space has a 16-bit identifier code, and the code for the current virtual address space is stored in this field here. When a trap occurs, which can either be an interrupt or a exception, interrupt processing or trap processing will occur. As part of that, the system status register must be saved, and that's the purpose of the stat2 register. So it contains a copy of the status register directly after a trap occurs. When a trap occurs, additional information will be saved. One thing that will be saved is the value of the program counter so that we can later return to the interrupted code, and that's stored in the register called prev-PC. In addition, there is a value that's stored in the cause register that will indicate what kind of interrupt or exception occurred. So the trap code is stored in the cause register. For some kinds of traps, we have additional information. For example, for an emulated instruction, we have the instruction that was executed, and that's stored in the CSR bad register. For a page fault, we have the address that caused the page fault stored in the CSR address register. And finally, we have the trap vector register. That should contain a pointer to the code that will handle the trap. So the kernel will set this before the trap occurs, and then at the time of a trap, a jump will be made to the instruction pointed to by the trap vector register. If virtual addressing is being used, then the page table register will point to the root of the page table tree. And finally, we have two more registers, the CSR pointer register and the CSR temp register. These have no special hardware functioning, but they are used by the kernel, and in particular by the trap handler, to implement trap processing. The pointer register is intended to point to a place where registers can be saved, and the temp register is simply a work register that can be used by the trap processing. There are two kinds of traps: exceptions and interrupts. Exceptions are synchronous events, like system calls and page faults, and interrupts are asynchronous events, like timer interrupts and interrupts from I/O devices. After the previously executing instruction finishes and before the next instruction executes, the hardware will do these actions when a trap occurs. First of all, the program counter is saved in a CSR called CSR prev-PC, and subsequently the program counter will be loaded from a CSR called trap vector. Presumably the kernel has preloaded that CSR with the address of the global trap handler function. So the next instruction that executes will be the first instruction of the global trap handler. Then the status register is saved in the CSR stat2 register, and after that the status register is modified. First of all, the interrupt enabled bit is changed to 0 so that future interrupts are disabled and cannot occur during the trap handling. Then the mode is changed to kernel mode if it was in user mode. And finally, if single stepping was enabled, that is turned off. A code which indicates which kind of trap occurred will be saved in the cause register. These trap codes are small integers, and they happen to be 8-byte aligned. The global trap handler will use the value in the cause register to dispatch through a jump table. So a jump table is an array of jump instructions, and each jump instruction happens to be 8 bytes at most. Many are just a single instruction, but at most 8 bytes can be used to access any address in memory. So the trap codes, which are 8-byte aligned, can be used as an index directly into this jump table, and so the global trap handler can jump through the jump table to the individual handler routine for whichever trap it is. Also, during the hardware processing, some additional information can be saved. For example, if it's an emulated instruction that caused the trap, then the offending instruction that needs to be emulated would be saved in the bad register. If it's a page fault or something else, some other things, the address that's causing the trap will be saved in the CSR called address. In the Blitz architecture, there's only a single bit called the interrupts enabled bit in the status register to control whether or not asynchronous interrupts are masked or not. There is no complex mask, multi-bit mask, or anything like that. It's just a single bit. Either interrupts are enabled or they are not. While interrupts are disabled, presumably the core is executing some interrupt handler routine, and we should not be getting any exceptions. If an exception happens when interrupts are disabled, that's considered an error, and it would be promoted to a so-called kernel exception, and then a new trap would occur. And so that would be basically some kind of an error within the trap handler itself. So what kind of traps can actually occur? Here's a list of all the traps along with the corresponding code. This is what gets stored into the control and status register named CSR cause. First we have the exceptions, and then we have some interrupts down here. The system call instruction takes an immediate value which can range between 0 and 1023. So there are a number of cause codes associated with the system call. Then we have an exception for arithmetic problems. Loads and stores must be aligned, and if they are not, then we have this exception here. Here's the null address exception. If there's an attempt to execute an instruction that is privileged in user mode or an illegal instruction altogether, we have an exception for that. And then we have a number of exceptions that are related to page faults, such as a write exception and so on. If the debug instruction is executed, then it will cause a debug exception, and likewise if a breakpoint instruction is executed, it will cause the breakpoint exception. If single stepping is turned on and interrupts are disabled, then a single step exception will occur. If there is a problem, namely an exception occurs while executing in a handler, or more precisely, while executing with interrupts disabled, then the exception will be mutated into a kernel exception. If there's an attempt to execute an instruction that's not implemented and that should be emulated instead, we would get an emulated instruction exception. There's a hardware fault exception, and we have something called a bad array index exception that supports error checking for array indexing. Beyond that, we have the interrupts for the I/O devices. We have the timer interrupt here, and then we have other things such as DMA completion interrupt and so on. In all cases, the cause code here would be used as an index into the jump table by the global trap handler. And as mentioned before, these things are evenly divisible by 8, and you can see that here. Next, let's talk about main memory and virtual address spaces and how the page tables are organized. This is where the Blitz architecture differs from other computers pretty significantly. Main memory is byte addressable, and multi-byte quantities like integers are stored in big Endian order. Program-generated addresses are 36 bits in length, and this means that we can directly address up to 64 gigabytes. This program addressable space is divided into 3 regions. We have the kernel address space, and we have the virtual address space, and we have the memory mapped I/O region, which is where I/O devices are mapped. The system itself can address up to 16 terabytes, but beyond this range, page tables are required. Blitz uses a fairly large page size of 16 kilobytes, but that has several benefits, and one is that it makes two-level page tables adequate. Page table entries are 64 bits in length, and I/O devices, which are memory mapped, can be mapped via page tables into virtual address spaces. Each virtual address space is given a unique identifier, which is a 16-bit value, and that's called the address space identifier. As I mentioned, all program-generated addresses are 36 bits in length. Normally, addresses like pointers and so on are stored as 64-bit values, but whenever a 64-bit value is used as an address, the upper 28 bits are simply ignored. With 36 bits of address, we can address up to 64 gigabytes. That 64 gigabyte addressable space is divided into two halves, and each half is 32 gigabytes. The lower half is called the kernel address space, and the upper half is the virtual address space. And when we have an address, the most significant bit, this bit here, is either a 0 or 1, and that determines whether the address refers to something in the kernel address space, if it's a 0, or in the virtual address space, if it's a 1. At any point in time, the processor is either running in user mode or in kernel mode. If it's running in user mode, then it's a user program executing, and only virtual addresses are allowed. So any address with this bit set to 0 is invalid when executing in user mode, and an attempt to use such an address will cause an exception, and presumably the kernel will abort the user program. When the code is running in kernel mode, then it doesn't matter what this bit is. It can be either a 0 or 1, and the kernel addresses as well as the virtual addresses can be used. Memory mapped I/O devices, such as read-only memory and other devices, are mapped into some place within the kernel address space, and by convention, this upper half, the second quarter here, is used for memory mapped I/O. Physical memory is mapped into the first 16 gigabytes, and if there is physical memory beyond that, it's mapped above the 64 gigabyte address. And that additional memory is only accessible through the page tables, as we'll see in a second. But the 16 gigabytes here should be adequate for most kernels and is accessible as part of the kernel address space. If the address has a 1 in this bit, then it's a virtual address, and it can be further divided into two fields. The lower 14 bits is an offset into the page. Our page size is 16 kilobytes, and so 14 bits is exactly the amount we need to address a byte within that page. The remaining 21 bits then is the page number within the virtual address space. Here's another way to look at what's going on. With a 36-bit address, we can access anything within a 64 gigabyte range, and that 64 gigabyte range is divided into two halves, the kernel address space and the virtual address space. Now there's only one set of physical memory, and that includes the memory mapped I/O devices, and those are all mapped into physical addresses within the kernel address space. But there are many virtual address spaces. Each virtual address space is described by a page table, and each address space has its own address space identifier. At any one point in time, there's one active virtual address space, and that's determined by whatever page table is pointed to by the control and status register called CSR page table. So if the code is running in kernel mode, that is if the kernel is running, it can access physical memory and the memory mapped I/O devices directly by using addresses within this range, and it can address any address in the virtual address space of the current virtual address space by using addresses in the upper half of the range. If the computer is running in user mode, then only addresses in the virtual address space, that is in the upper half here, can be used, and whichever address space is accessed is determined by the current values of the pointer to the page table and the address space identifier in the status register. A page table is a data structure in the shape of a tree. In Blitz, the page tables are only 2 levels, so here we see that. At level 1, we have the root node, and at level 2, we have some additional index nodes. And at the lowest level, the leaf level, we have the actual data pages. Each node in this tree is 16 kilobytes in size, and the entire tree is kept in physical memory. That means these addresses, these pointers here, are pointers within the kernel address space, because the tree is living in physical memory, and they're not mapped virtual addresses. Here is a picture of a virtual address. It's 64 bits, and this bit must be a 1 if it's a virtual address. Here I'm showing the exact same information. The remaining bits are broken into these 3 fields. As I mentioned, the lowest 14 bits is a byte offset into the data page itself, and the remaining 21 bits is the virtual page number. That's divided into 2 parts. The upper part, which is VPN1, and that's a 10-bit field, and then we have VPN2, which is an 11-bit field. Here's the same information with our 14-bit byte offset and the virtual page number, part 1 and part 2, and of course this bit would be a 1. In this image, I'm showing a path from the root node all the way to the data page. Each index node, whether it's the root node or a node at level 2, is an array of page table entries. There can be up to 2048 page table entries in an index node at level 2, and to access or to index into this array, we need an 11-bit number, and that's exactly what VPN2 is. So we can use VPN2 to index into this node here. And with the root node, we only have 1024 entries, and we only need 10 bits to address into that. So if this is a full 16 kilobytes, then the second half is not used and available for other information to be stored by the kernel as it needs. So to take a virtual address and locate a byte, we use the VPN1 field, which is 10 bits, to access a page table entry. That will contain a pointer to another index page, and we use the field called VPN2 as an index into that array to access the next page table entry. And that will then contain the actual address of the data page itself. And we've used the final 14-bit offset to index into the data page to get the byte that we're interested in. Each of these page table entries contains not only the address, but some additional bits, which we'll talk about in a second. When a virtual address is presented to the hardware, that is, when an instruction is executed that uses a program-generated address with a 1 in this bit, and therefore that is a virtual page, the hardware will walk the page table to locate the appropriate data page and use the offset to access the byte within that data page. And that will all happen in hardware. That walk will happen in hardware. So the instruction is not aware that it is getting mapped from the virtual address into a physical address somewhere in that 16 terabyte physical address space. Here's the layout of the page table entry. Remember that a page table is a tree of nodes. At level 1 we have the root index page, and at level 2 we have some additional index pages. Each index page is an array of page table entries. So we're showing in detail one of these page table entries here. The page table entry consists of a number of fields. This 30-bit field here is the physical page number, and then we have some additional fields over here. With 30 bits, we can address a large number of physical pages, 2 to the 30, in fact. That's about 1 billion. Remember that each data page is 16 kilobytes. We use a 14-bit offset to address any byte within a data page. So combining these together, we have an address space of 2 to the 44th, which means that in the Blitz architecture, we can have up to 16 terabytes of installed physical memory. Remember I showed this picture here where the physical memory in the lowest part is directly accessible. I did not show additional physical memory, which would be located above the 64 gigabyte boundary. But the root page of the page table, that is this page here, must be in this region, but the index pages and the data pages can be anywhere in installed physical memory. So now let's look at the additional bits in the page table entry. The valid bit is used in page table entries both in the root node and in the level 2 index pages. So it's used both in these page table entries and in these. The other bits are not used in the root node, but the valid bit tells whether that memory is actually mapped into the virtual address space. Then we have the executable and writable bits, which indicate the permission for that data page. Can the bytes in that data page be executed, or can the bytes in that data page be updated? Here we have a bit that indicates whether the bytes have been modified, and if the page is clean, then any attempt to write to the page will cause an exception so that we can set the dirty bit. And finally, we have a copy on write bit that will cause an exception if we attempt to write to a page that should be copied. The remaining 29 bits are reserved for kernel use and can be used as necessary by the kernel code. At this point, we can turn to the instructions. For example, we have the add and the add immediate instruction, and here you see their opcodes as well as their assembler notation and what they do. There are quite a few instructions, as you can see from this list, and we don't have time to go over all of these instructions here. In fact, that is the subject of another video. Instead, I will refer you to the website that describes the Blitz system. On that website, you can find full documentation for the Blitz-64 design. The material that I've been discussing here comes from the Instruction Set Architecture Quick Reference document. You can also find additional videos about other aspects of the Blitz-64 system. Well, that's it for this video. Thanks for watching.